Hi everyone. So I'm Allan Green. I'm from the SBRC at the University of Wollongong. I'll just check that this is working. And today I'll be presenting on a recent pilot project that we did together with the Resilient Building Council, looking at parallels and co-benefits between retrofitting for resilience, or bushfire resilience in particular, together with energy efficiency and sustainability. So the slide on the screen is just showing a bit of an overview of the previous 30 years or so in Australian building regulations and the parallels between provisions to improve or to set minimum standards for bushfire resilience above the timeline and energy efficiency below the timeline. So before 1990, for both of these aims, there was fairly little done in terms of minimum standards in Australia for new buildings. There was quite a lot of knowledge, especially in the energy efficiency front, but it was really a niche activity to build an energy efficient building before 1990. And then moving through the 90s, we started to see some minimum standards being introduced with AS 3959 in bushfire and some minimum standards in different states for energy efficiency. Then moving into the 2000s and 2010s, those minimum standards were incrementally increased on both fronts. And so what we've seen is this sort of general improving in the standard of Australian buildings over that period. But what it's left us with is this legacy of poor performing buildings that are vulnerable to bushfire and have very poor performance in terms of energy efficiency. And so this is really to do with climate change. On one front, we're trying to reduce climate change and stop it in its tracks as much as possible. And on the other hand, we're trying to adapt to the effects that we're already starting to see. And to address the legacy buildings, typically what's done in both fronts is to retrofit existing buildings to increase their standards. So put insulation in buildings for energy efficiency, make small design changes, and put up ember screens and that kind of thing for bushfire. So to give a bit of a context on the energy efficiency side of things, there's a concept called embodied emissions, which is starting to become more and more important when we look at the overall carbon footprint of a building. So this is some images of the Fortis House, which was designed during a community-led project led by the Resilient Building Council recently. And the graphs on the right are showing some analysis we did of that house design, looking at the carbon footprint of that design, and it's broken down into the embodied carbon and the operational carbon. And so the operational carbon is all of the emissions that come from running the building and heating and cooling it through its operational lifetime. And the embodied carbon are all the emissions that are attributed to the production of materials, the transport of materials to the site to build the house, building the house, and then at the end of life, disposing of all those materials. And so really what we're showing here is that moving down those bars, we're starting to move from what was minimum standard practice in Australia prior to NCC 2022, and then lower down at 7 stars, we're starting to look at what's minimum standard now. And so this relative size of the embodied carbon contribution to that carbon footprint is getting larger and larger. And really importantly for this as well, the Australian electricity grid is changing rapidly at the moment. So that graph on the left is showing the projected carbon intensity of the Australian electrical grid over the coming decades. And so we're really in a period of rapid transformation where the operational emissions from heating and cooling our buildings is becoming less important, but the embodied carbon is becoming more and more important. And so the tool that we usually use to assess this in a building from an energy efficiency and sustainability point of view is a life cycle analysis. So along the top of this slide, you can see the different stages of a building's life, in inverted commas. And during its operation, there's those operational emissions that I mentioned, and that typically is what's looked at for energy efficiency assessments. But then when we conduct a life cycle analysis, we draw a much broader net, and we capture the green operational emissions, but also the blue embodied emissions. And so they're all the components shown in blue. And then what was novel in this study that I'm presenting on today is that we also looked at what's drawn in with a red arrow in the slide, and that's is a probability for every building that during its operational lifetime it will be damaged or destroyed by a natural hazard. In this project, we were focused on bushfire. So there's a probability that a house will be destroyed by a bushfire and then need to be rebuilt with new materials. And so this is the key concept that we were looking at in this study. Those new materials that are needed to rebuild the house have their own embodied carbon. So including that in this life cycle analysis, we can then start to tie in resilience and how important resilience is from a carbon emissions point of view. So I think Kylie Steele presented on or mentioned the pilot project that I'm talking about yesterday as well. So it was a relatively small study, just looking at 29 homes, but in quite a lot of detail. There were 15 houses from New South Wales and 14 in Victoria. Each house had a bushfire resilience star rating assessment undertaken, as well as a resilience efficiency scorecard rating, which is like a energy efficiency assessment. At the SBRC, we developed a new method to calculate the resilience impact on the overall greenhouse gas emissions of the building, which was what I was showing on the last slide. We conducted a life cycle assessment of each of the houses based on the data collected on site. And then we were looking at two main things in our part of the study. We were looking at the potential co-benefits and conflicts when you assess a house for retrofitting for both energy efficiency and bushfire, to look at are there any challenges that you come up against, or are there any opportunities to draw sort of mutual benefits from a single retrofit. But we also looked at that greenhouse gas picture and to look at when you're retrofitting for both purposes, are there any added benefits? What impact does that have on the carbon emissions? So I won't spend very long on this. This is sort of the high-level equation that we use for that calculation. So it's pretty simple overall, but behind each one of these symbols there's a sort of integral equation which we need to solve numerically through time. So we're calculating the overall impact of a retrofit on the greenhouse gas emissions of a building. There's upfront carbon emissions involved with actually undertaking the retrofit, so you're using materials that has an impact. Then there's the change in the operational emissions that you're causing by that retrofit. So that includes the reduction in energy needed to heat and cool the building. We need to factor in the decarbonisation of Australia's electrical grid in that calculation. The age of the building at the time of assessment is important because some houses might have only a few years left until they're demolished anyway, whereas others would be operating for much longer if it's a newer building. And that calculation also needs to include the probability of being destroyed by a bushfire, because if a new building is built in Australia currently, it's built to current standards. And so if it is destroyed by a bushfire in the calculation, it's built to a higher standard, and therefore the energy efficiency is also impacted. And then the last group of terms is the change in those the embodied emissions associated with potentially needing to rebuild after a bushfire. And so to draw that out in a bit more of a clear way, if we picture an example house that was built in 1990, we conducted this study in 2022, and we were looking at the remainder of its operational lifetime, so that would take us to 2065 if we assume it has a 75-year operational life. And we looked at the sensitivity to that assumption later on. We then calculated the operational emissions through that remainder of its lifetime, as well as the emissions to do with the probability that will be destroyed by a future bushfire. And to do that calculation, we looked at the historic bushfire frequency at each location. we assumed that that continued into the future, and that was another assumption that we looked at the sensitivity of, and I'll show you some graphs later on that. And we looked at the specific construction details of the building as well, so we assumed it would be rebuilt in a similar sort of size and form to its current. And in the operational emissions calculation, we factored in that decarbonisation of the grid. And then we compared that to the same house, but with an intervention undertaken in 2022, where both assessments were undertaken and the house, all of the suggested retrofits were applied to the building. Those retrofits have their own embodied emissions, which we calculated. And then there's the modified operational emissions and emissions associated with resilience that we calculated for that other case. And then by comparing the two cases, above the line and below the line, we can look at the impact of the retrofit overall in a more holistic sense. So this is a snapshot of some of the results that we saw for the individual components of that calculation. And so the horizontal axis on these graphs is embodied emissions in terms of tonnes CO2 equivalent. The left-hand graph is showing all of the bushfire retrofits which were recommended by the tool for the 29 case study houses, and on the right is the energy efficiency retrofits that were recommended. So I guess the highlight results here are that the order of magnitude can be up towards sort of 10 tonnes CO2e just for a single retrofit. So there are significant impacts, but a lot of retrofits are very low impact. For example, installing mesh over openings, sealing gaps in walls and that kind of thing, where you're not using much material. Some materials are more energy intensive than others, and therefore more carbon intensive. So aluminium window frames are really high energy intensive. And there is quite a lot of variability between different buildings as well, which we're seeing on this graph. Another element in that calculation is the emissions abatement through the energy efficiency retrofits, and that's what's shown in this graph. So again, the horizontal axis is the change in CO2e caused by each of the retrofits. And again, the highlight results are that the order of magnitude is sort of in the tens of tonnes. So these retrofits were having fairly significant impact in a lot of cases. But it's important, one caveat in this study, I suppose, is that the scorecard tool, which we use to prescribe retrofits, isn't optimised to recommend retrofits which will reduce carbon emissions. It's optimised to save homeowners on their energy bills. And so usually the two are correlated, but I suppose there are a few types of retrofits which are being recommended by the tool which don't necessarily have a large or any impact on carbon. So one example of that is that houses with fuel burning stoves or wood burning stoves in our calculation have a fairly low impact because they're using a renewable resource, but the tool recommends that they get replaced with a new heat pump, which is higher efficiency. And then this piece of the results is really what was new in this, and it was enabled by the bushfire star rating system, which quantifies the probability of loss of a house with each assessment, or an estimate of that probability. And that's what enabled us to look at what's the reduction in probability of loss caused by each set of retrofits. So each of the entries in the graph is representing one building, going from the orange dot, which was the state that it was assessed in, down to the blue triangle, which is where we were predicting it could be brought through the retrofit. So the axes on that graph are the probability of loss on the horizontal and the embodied emissions associated with being potentially destroyed by future bushfires in the vertical. So I guess the highlight results on that graph are that the tool was predicting really significant reduction in loss of property through the retrofits that it was recommending, and there is a strong correlation between that and the carbon emissions associated with having a poor or good bushfire resilience. And then these graphs are really showing the overall picture, and that's our main result. So they're showing the build-up for each of the properties of those different components and what the net impact would be on carbon emissions. So the black and the red bars are showing the embodied emissions that are associated with the materials you're using to undertake the retrofits. And in most cases, that's offset by the benefits you get in terms of operational carbon emissions abatement, as well as this extra element that we're introducing in this study, which is the bushfire resilience emissions abatement. One thing that we really noticed was there's a huge variability from building to building, and there's no clear correlation between building age when it was built and the result. But probably the most important and most interesting result is that the white bar, which is the component of this new element that we're introducing into the life cycle analysis, is pretty significant in a lot of cases. And so that's the carbon emission abatement that can be achieved by retrofitting for bushfire resilience. I won't spend very long on these graphs, but it's just showing some sensitivity analysis that we undertook to look at some of the key assumptions. So we assumed that all the buildings would have an overall lifespan, operational lifespan of 75 years. And obviously, if you assume the building's going to be around for longer, it'll impact the results. So that's what the left-hand graph is showing. And the graph on the right is showing the sensitivity to the assumed future bushfire frequency. So we took a really simple assumption in these calculations that the historic recorded frequency would continue into the future. So as a result, actually a few of the properties didn't have any recorded bushfires within a 1 kilometre radius. And so in our calculations, they had a 0 future bushfire frequency. But if conditions change into the future, or if that historic record isn't 100% accurate, then the right-hand graph is showing how sensitive the results are to that assumption. And so this is my last slide. I guess the caveats on this study are that it's a really small sample size. It was really just an initial pilot to look at the feasibility of this idea. Are bushfire retrofits having a substantial carbon emissions abatement impact? And what we found was that for a lot of properties that we looked at, they were, or they would. So it's showing that in addition to the benefits that we already know in terms of life and property safety, and adapting to climate change, retrofitting our legacy buildings for bushfire resilience can also have a significant carbon emissions abatement, which is helping to combat the root cause of the climate change. And the other finding that we had from this study, which I didn't present much on today, was by looking at the potential conflicts and co-benefits of undertaking these retrofits together as a one operation, looking at bushfire resilience and energy efficiency, there are quite a few co-benefits, and there are quite a few inadvertent adverse effects that you can avoid as well by, for example, installing polystyrene insulation under a floor for energy efficiency in a bushfire-prone area. By undertaking retrofit programs for both aims together, you can avoid those sorts of issues and also unlock some co-benefits. So the next steps for this study are to expand it. We're currently working as part of the Resilient Building Council multi-hazard efficiency and energy efficiency home assessment tool program, which is being presented on this afternoon. So this carbon picture is being introduced into that project as well. We're planning to extend the analysis to also look at flood and cyclone and storm, because similar effects are probably apply there as well, where buildings could be destroyed or damaged by those other disasters. And we're planning to extend the analysis to a larger set of homes as well. So we're looking at a study of about 300 to 400 homes to get a bit more of a representative sample. And also, while this program was looking specifically at new builds, there's probably similar findings to be found for new build. Sorry, if we're looking at retrofits, there's probably similar results to be found for new builds as well. even though new builds are being built to a higher standard today, there's still small design choices that can be made to make them more resilient to bushfire and other disasters. And so potentially those choices when you're designing a new house can have a significant impact on our carbon emissions as well. So that was my last slide. Were there any questions?
That was really interesting. Thanks for that presentation. Was there any bushfire retrofit measures that also had any energy efficiency improvements linked, like as just standalone bushfire retrofit?
There were very few that had direct co-benefit, so an automatic co-benefit, but there were quite a few where by undertaking one retrofit, it sort of opened up an opportunity for another. So windows are a good example of that. If you're replacing your windows to be toughened glass, then getting double glazing is almost a no-brainer. And there were quite a few of those sort of inadvertent co-benefits or opportunities being opened up.
That's the second question. What were the sort of top 3 energy efficiency upgrades on retrofits that sort of had the most impact?
For energy efficiency, I'll flick back in the slides if I can.
White section is bar graph.
No, so the white section was the, in the bar graphs was the benefits from having a higher resilience. I think the question was about energy efficiency. Yeah. Oh yeah, thank you. So installing new heat pumps was one of the highest, so upgrading the efficiency of your appliances was very effective. High performance windows, upgrading wall insulation, they're probably the standout retrofits.
Hey, right next door. I was wondering if all of the bushfire retrofits and or energy efficiency retrofits, then you looked at the impacts for that on the lifespan of the building itself in the interest of retaining existing housing stock for longer rather than our current model, which seems to be just bulldoze everything and build something new and generate more industry that way.
Yeah, and that's a really good question. We didn't look at that at all, but obviously if you're undertaking a retrofit on your house, you're upgrading the quality, potentially extending the life, and that wasn't included in the calculation. No other questions? Thank you.